Okay, so today we're going to talk about comparametric equations. So comparametric equations are equations that allow us to compare differently gained quantities of the same thing. So we might have something like f of q compared with f of some constant times q. And so we all know what a parametric equation is. So a parametric equation is like when you have, say we have x equals cos t, where t is the parameter, and y equals sine t. Then we have a comparison between x and y that defines this shape of a circle, from 0 to 2 pi, just goes around. And so this is called a parametric equation. A comparametric equation is an equation in which we have something like, we have, instead of, here we have, if we had tables of x and y, we might have, cos t and sine t. Now with a comparametric equation, we'll have similar kind of idea, but instead of here we'll have, this will be f of some quantity q, and this will be f of some quantity kq. And so we'll have this relationship. You'll have your plot here in a comparametric equation. Your plot analogously is something like this. You've got f of q here and f of kq here. So this is, and we usually call that g. G equals f of kq. So we have f of kq as a function of f of q. That's called a comparametric equation, parametric plot. So let's take as an example, say f of q equals q squared, and then g equals f of kq equals kq squared equals k squared q squared. And now what do we recognize? This is k times k squared f. So now we have g equals k squared f. So this is a relationship between f and g that does not involve q, and that's called a comparametric equation. And so if we plot that out, this comparametric plot, we simply have the straight line of slope equal to k squared. So oftentimes we're comparing things, like we're comparing in the photographic universe. We're using things like cameras. And so if we take a camera as our point of reference, I have to open this thing up a little bit here. Kind of get it, tease it open just a little bit. There it goes. So this is a camera, for example, and it's a Kodak camera. And so if we look on these cameras, they have shutter speeds and apertures and so on. And in a sense, a camera is a measuring instrument. So it'll have a shutter speed like 1/400th of a second, 1/200th of a second, 1/100th of a second, 1/50th, and 1/25th.
I'll get a close-up shot. Okay, let me focus again. Okay, yeah, it's in focus now.
So you can see 1/400th, that's f of q. 1/200th is f of 2q. 1/100th is f of 4q. If you do an exposure at 1/50th, it's f of 8q, and at 1/125th of a second, it's f of 16q. It's measuring the same thing, differently gained. And so this is kind of the idea. This is how cameras work, is that they do things in exposure. So if we were looking at, if we had this series of pictures, we're going to have something like, we're going to have this kind of construct where we've got, we've got Q, we've got an exposure 1 at Q squared, or K squared, 1K, K squared. This is just K to the 0. And, K cubed and so on, K to the 4th. And so what we see here for K, in this case, K has a value of 2. So we've got 1, 2, 4, 8, and 16. And this corresponded in terms of exposure time. This was 1/400th of a second, 1/200th of a second, 1/100th of a second, 1/50th of a second, and 1/25th of a second. So what we had there was an ordered list of gain settings on this camera here in terms of what it is capturing. And if we look at that in terms of exposures, we're going to have some function. The image is some function, a picture is some function of some quantity Q of x and y, and more generally, comparametrically, versus some function of k times q of x and y. And we can compare this, we'll call this is called G. We usually use, just like in when we're plotting something, we'll have XY pairs. When we do normal, traditional plotting, these are functions now. This is functional equations. So we have F, and then the next letter of the alphabet is G. And we have this relationship between F and G that a comparametric relationship is this relationship between F and G, which is F of KQ, that doesn't involve Q. So just as a simple example. So if we take, let's just go through another quick example so we understand, we can develop this a little bit simply. Let's say we have F of Q equals alpha times Q to the gamma, and then G of Q equals F of KQ equals alpha KQ to the gamma. And so that is equals alpha K to the gamma Q to the gamma. And that is equal to K to the gamma times alpha Q to the gamma. Now what we notice here is that this is just F. So this is equal to K to the gamma times F. So now we have G. Again, this is a comparametric equation. This is a relationship between F and G that doesn't involve Q. So to solve a comparametric equation, we could ask the question, what is, if I got rid of this, if I didn't have this, if I say for a moment I didn't know what that was right there, and I wanted to ask the question, that was all blank, let's say, and I didn't know how this equation came about, but I just told you that I'm thinking of an equation here. This is G equals K to the gamma F. And I'm going to ask you, tell me what F of Q is when this is the relationship between G and F. So what the camera does is it gives you pictures, but it doesn't give you the underlying relationship mathematically. So here are my pictures, for example. I've got G equals K to the gamma F. And I'm going to ask you, what produced that. So to do that, to answer this question, is to solve the comparametric equation. This is a comparametric equation, and we want a solution for it. So that's kind of fundamentally what comparametric equations are all about. Now, let's take another example here. I'll just take another example. Let me get another piece of chalk here. So let's say that we have f of q is equal to alpha plus beta q to the gamma. And then over here on this side, I've got g of q equals k times, you just change, it's going to be alpha plus beta k q to the gamma. So we just substitute in q becomes kq. So now if I look at this, this is equal to alpha plus k to the gamma. It's multiplied inside times beta q to the gamma. Now, if we want to try to bring these together and desolve this comparametric equation, if you will. So if I'll go g minus alpha is equal to k to the gamma beta q to the gamma. And over on this side, I'm going to go f minus alpha equal beta q to the gamma. Now, what do we notice? We can see there's a pattern here that's pretty similar, pretty obvious. This is just k to the gamma times f, so we can see that this is just k to the gamma times this part right here is the same as this part here. So this is just this over here, and that is f minus alpha. So I've got g minus alpha equals k to the gamma times f minus alpha. And if I take the g on one side, isolate it, g equals, let's say, I'll put it right here, I'll put the alpha first, g equals alpha plus k to the gamma f minus alpha. And I can kind of carry this forward a little bit. It's alpha plus k to the gamma f minus k to the gamma alpha. And now that equals, I can take the alpha outside here. Alpha minus alpha times 1 minus k to the gamma. And plus k to the gamma f. So I've got here a constant, and so I can just I can say that is equal to a plus bf, where a is defined as this. That's a here, and b is defined as k to the gamma. So I've got now a very simple comparametric equation here. This is just a simple comparametric equation that says g equals a plus bf. That's a comparametric equation. Very simple. It's a very simple comparametric equation, and its solution, the solution of this comparametric equation is this: f equals alpha plus beta q to the gamma. So this here is a solution to that there. And so normally, of course, it would be the other way around. We'd say, okay, this is a comparametric equation. I'm going to ask you, what is the solution to that comparametric equation? Then you're going to tell me, that's the solution. And so now, if I were to plot these, let me take this and plot these functions here. Let's plot these functions out. And I'm going to simply say, okay, here we go. So here is f, g, and it's just a straight line. with an intercept A and a slope of B. Very simple. So that's just a straight line. So that tells me the comparametric equation is a straight line. And you can think of many other examples of comparametric equations. Now, another important thing to consider with comparametric equations is there's a family of solutions. Just like when you solve integrals, you know, when you integrate something, you have a family of possible solutions. So if you have, you know, an integral, like, I'll say I have y equals x squared and dy by dx equals 2x. You know, it's so simple. But if you go the other way around, if you started with 2x and then you take the integral, you know, you're going to get your x squared, but you're going to get plus, you know, some unknown constant. So there's a family of solutions that have the same derivative, because if I have, you know, y equals x squared plus some constant dy by dx is the same. So the slope of that line, so that's simply saying that when I have this function here and this function here, they both have the same slope. So there's an ambiguity when you take integrals. When you take, equivalently speaking, when you take derivatives, you're destroying information. Differentiation is a high-pass filter that destroys information. In particular, it gets rid of the DC content. There's a, you know, the electrical component that does this approximately as a capacitor. It approximately does this integrating, and it destroys the DC. So if you have a battery here, you know, feeding into this capacitor, and then you try to measure the voltage out of here, you get 0 volts DC over here because the capacitor is differentiated. It's taken the derivative and thus thrown away or disposed of the DC offset. So you've lost some information there. And equivalently with comparametric equations, cameras destroy information. So when we have comparametric equation, let's take a simple example that say f of q equals q squared, and then we'll have g equals k q squared equals k squared q squared equals k squared f. So we've got g equals k squared f. Now let's take another example. F of q, take another example, equals 2 q squared, and then g of q is equal to 2 times kq squared, which equals 2 times k squared q squared. And now what we have, this is equal to k squared times 2q squared, and this is just f, exactly. So now we have that g equals k squared f from over here, and that's the same comparametric equation. So you see we've got two identical comparametric equations that came from different things. So that tells us that these are both solutions to this comparametric equation. So if I gave you a comparametric equation and I said g equals k squared f, where that's some constant, then you've got, you know, multiple possible solutions. So oftentimes, oftentimes k equals 2, or sometimes k equals the cube root of 2, you know, third f-stops on some cameras, or f-stops, for a lot of cameras k is equal to 2. So if I gave you something like, say, g equals 4f, and I said, okay, solve that for me. You've got many, many different possible solutions. In fact, generally, if I just take f equals beta q squared, and then I'm going to say that you're going to get g equals beta kq squared equals beta k squared q squared equals k squared beta q squared, and again g equals k squared f. Same thing. So you can see that this family of functions comparametrically is the same. In other words, this comparametric equation evokes a family of solutions. So my point is that the solution of comparametric equations is not unique. And cameras or imaging gives you comparametric relationships. So we're surrounded here by comparametric relationships, comparisons. As we saw before, what we're going to do is I'm going to show you a couple of things that we're doing with comparametric equations. So we've got this meter, this measuring instrument. We made a really quick, simple measuring instrument, and I've got some lights here. So what I did is I got an ohm meter here, resistance meter that measures resistance, and I've got it connected to a photo cell, and this was kind of the quick homemade light meter. So this is a cadmium sulfide cell, a photoresistor, a light dependent resistor, and it is connected to this multimeter here. And so in a sense I've built a really crude and awful light meter. I kind of wanted to build a really awful, crummy light meter to show how comparametric equations work. So this light meter captures light, but it captures light in some strange function. So it has some strange function f that we don't know of the quantity of light q. And so we don't know what f is. So we're measuring, and it measures in ohms and resistance. But what we're really trying to do is measure light. And so let me just briefly explain what we're trying to do here by way of a couple of examples. So one thing is, we saw before if we had a light bulb, and what I did is I covered up half the light bulb, so we would be measuring, we've got this, say this is my light bulb here, and we would cover up half the bulb and have half it lit up and the other half dark, and then have the cell here, and then that would give us some function of the quantity of light. And what we were doing basically, if this is the photoresistor here, we'd be simply cover up half the light, and then move, like first not have the light covered, measure what the resistance is, then cover up half the light and move this closer until it comes to the same number as the entire light, and then uncover that half and look at the number, and then cover it again and move it into that number, and so on. And each time we did that, we're taking this comparametric relationship. So this is basically a numerical solution of comparametric equations. There are sort of three basic ways to solve comparametric equations. We can look them up in a table, or we can solve them directly, or we can do a numerical solution. So we can look in a table of comparametric equations, much like a table of Laplace transforms, and try and solve the comparametric equations, or we can solve them directly, or we can do this numerical solution. And when we're doing a numerical solution, what we were doing, one way we sort of physically did it is to understand it this way. This is a really good way to understand it as this light meter that we built. So here I've got, for example, now instead of covering up half the light, another way to do it is to have two lights here, and then we take one of the lights and we take the light source and the photocell. I've got the photocell here, and do the same, play the same game here as we did with the photocell, where we've got, let's say it's sitting right here, and it's showing a certain resistance, and we would just simply take this light here and hold it up here and see that it's 167 ohms, and then we unscrew one of those lights, and then it would go up in resistance, and we move it closer until it's 167 again, and then decrease it. Going the wrong way. Put it over here actually, see if you can see that. Probably a little easier to see this way. So we take both these lights, and I look at that and I see, okay, it's 75 ohms, and of course we do this in complete darkness rather than have the lights on. We see it's 75 ohms, and then I unscrew one of the bulbs, and then it goes to higher. It goes to 97 ohms or something. We keep moving it closer and closer and closer until it comes back down to 75 ohms again, and that's right about there. And then we'd screw the second bulb in, and it goes up to 54 ohms, down to 54 ohms, and then we'd unscrew this and bring it even closer until we got to 54 ohms, which is about here, and then we'd screw the second one in again and see, okay, it's gone down to 35 ohms, and so on. And this is K equals 2. We're doing this now. If we this has a place for 7 light bulbs, which are all radially symmetric except for the one in the middle. So if we look at this, there's a place you can put 7 bulbs in, and then we can see this here. We got 7 light bulbs there, and let's go to 7 bulbs, and then there's one in the center that we simply don't use, because this way they're all the same distance. So if we come to the photocell, if we're here, each of these is equidistant to the photocell and shining in at exactly the same angle. So each of these 6 lights will affect the photocell exactly identical. So we've got our 6 lights here, and then the one in the middle, we don't want to use that. So we just want to use only these 6, because they'll respond equally. And so what I did is I simply typically I used to just have 6 bulbs that were all the same, 6 brand new light bulbs that were all bought at the same time from the same vendor with consecutive serial numbers on them, so they're pretty identical. And then I'm going to take these 6 bulbs, and what we do is we simply plug in 6 light bulbs that are all the same into this fixture, and this. Bulbs like this, and then we got 6 lights. And you see now what we can do is we can have different combinations of light. We could have 1 or 2 or 3 or 4 or 5 or 6. What's really magic, the most magical combination, I think, is to have 6 lights and then just unscrew only one of them to 5 lights. So now if I look at this here, it is now 38 ohms, 38.4. Now I'm going to unscrew one light, and it goes up to 40 ohms, 38, a little bit more, and then we're going to come back in until it's 38.4, again the same amount, and we're going to screw that one in, and it'll drop down a little bit to about 30 ohms, and then we unscrew one of them and then advance it back in until it comes back down like to the same 30 ohms or so, and then screw that in, and we see it goes to 26 and so on. Of course, this is not very accurate because I'm not doing it in the dark, but you can see what I'm doing there is this time, what's different about what I did this time is that now the change in light is so much less. See, so you can see what I've got here is I've got this when 5 lights are running, let's call that 5Q. So we're going to have, we're really comparing f of 5Q versus f of 6Q. And more generally, we could say I've got f of Q versus f of KQ, where K equals 6 over 5, which equals 1.2. And so we've got a 20% increase. Rather than a doubling, we've got just a 20% increase in the amount of light. So that gives us this beautiful power. I'll just move these out of the way for a moment. So now we've got this doubling of the amount of light is what we used to have, and then we went to a 20% increase. So you can think here we've got K, in this case, equals 1.2. And so we've got a smaller increase. And more generally, we could take an infinitesimal. We could say let K equal 1 plus epsilon, where epsilon is some small number. If we had 101 lights and we turned off one light, we'd have 100 lights. And then we get F. So if we had F of 100Q versus F of 101Q, we've got a 1% increase in the amount of light. So we got a very fine increment by which we do our experiment. This is like a numerical solution. You can see it's approaching infinitesimals. And I just want to say, I'll move this out of the way here. I just want to say, you know, we did some work with one of my students, Adnan Ali. He, a super genius student, he discovered this important link between comparametric equations and quantum field theory. And this is, we published a paper together on this comparametric camera response functions and so on. And so what he discovered was this link, you know, between these infinitesimal operators. And so he's quite a really genius guy. He built, when he was 12 years old, he built a cathode ray oscillograph out of a glass tube, and he had a broken fluorescent light he got the phosphor out of to put on a piece of glass, and he had a vacuum pump, pumped all the air out of it after making an electron particle accelerator in there. And he made a cathode ray tube, cathode ray oscillograph, from scratch. And so super genius guy came up with all these relationships. So if you get a chance to read over, we're going to bring him in as a guest speaker this coming week on Thursday or Friday. So I'll be having him come in to do a guest lecture, which we'll record. So the idea here is with comparametric equations, we're kind of figuring out this relationship numerically in this case, in this particular example with the light bulb. And so let's think about what we're actually doing. We've got f of q here, and we've got, like this might be f of 1.2q or f of 2q, or generally f of kq here. And we've got some function here that we don't know, and we're trying to solve this. So we're going to take some amount of the initial amount of light when we make these entries. We've got this, you're going to be having this entry f of q and f of kq, and you're going to have some number of ohms or resistance or conductance. You probably want to do 1 over resistance. It'll be a little bit easier to understand as conductance, but you're going to get some number here. Put in some number here, and then you're going to double the amount of light, like uncover half the light or turn on the extra bulb or whatever it is. And so this is going to be kq, and then you put a number here, and then you bring this number over here, and then you again uncover. You can use a foot switch or something, or a friend can turn it on and off for you, or cover and uncover it. And you build up this map here, which is ultimately a list of numbers. And so if we think of what's going on here, if this is some quantity q0, say this is f of q0, and then over here we've got f of k times q0, and then if I just draw a circle around here, just draw an arc over here and take this, whatever this distance is, and put it over here, and then now this is f of q1, which is f of k q0, so q1 equals k times q0. So now this is f of q1, and then we're just going to go up to the curve and come across, and then this is f of kq1, which we'll call q2. And then you just again take that thing back down here and come exactly the same amount over here, and then go up to here, and then come over, and then draw a circle, and then come up, go over, draw a circle, come up, go over, draw a circle, and you just keep going like this. And this is kind of unrolling or unwrapping this comparametric relationship. That's exactly what you're doing here. And you just keep going like this and solving it. You can see that if you could use a smaller comparametric ratio, a smaller value of k, you could do this at finer and finer increments. And you literally be solving that differential equation in you're almost building a piece of apparatus that solves the underlying differential equation that's related to the comparametric equation at an infinitesimal level. So I want everybody to really understand this lab and the power of comparametric equations to understand things that you can't immediately measure or are difficult to measure, or it's a simpler way than measuring. It's a very easy way to kind of understand the world around us comparametrically. The other concept that we're going to get into is that when we have pictures, you're going to be taking some photographs. So let's say we were to take a picture at some shutter speed, like a 400th of a second, and then you take that exposure at a 400th of a second, and then without moving your camera, you change it to a 200th of a second, take another exposure, and then keep the camera in the same place and change it to 1/100th, and then exactly the same time change it to a 50th, and so on. So you're going to get these pictures, and then when you have these pictures, you're going to want to compute what we call comparagrams from those pictures. So this is what we're going to do, is we're going to generate comparagrams. And let's take a typical example. Let's suppose we had, for example, a 2-bit camera, 2-bit depth. It only does a 0, 1, 2, or 3 are the only values that it can output. And let's say it's a 12-pixel camera. And the array is 3 by 4. So it's 3 pixels by 4 pixels that each have 2 bits. And let's say we had an example. We had 2 images, a darker image and a light image. And let's say we had, I'll just make up something here, we had 1, 2, 3, 2, 0, 1, 2, 3, maybe 0, 0, 1, 2, and then this brighter image over here, let's say it was 2, 2, 3, 3. So this image will be slightly greater exposure. 1, 1, 3, 3, 0, 1, 2, 3, let's say. Now we want to compute the comparagram between those two images. So the comparagram asks us this question. It's a plot of domain versus range. Remember, this is, in a sense, this is a sampled version of f of k, q of x, y. And this one is f of q of x, y. And we're trying to plot this comparagram is a series of, so let's say this is f, and this is g. So this is the domain of this image is down here on this axis, and the range is this image over here on this axis. So this image is on this axis, and this image is on this axis. So we just go through pixel by pixel. So I'll divide this up into boxes. A matrix is just a box of numbers. And I'm going to say, okay, 1 and 2. So this is 0, 1, 2, 3, 0, 1, 2, 3. And we're going to say at coordinates 1 and 2. So we're going to go over 1 to pixel value of 1 and up 2 to here. So this first one is, so we're going to add 1 to that. And then we're going to go to the next one. So 2 and 2. So 2 and 2 is right here, so we'll add 1 there. And then we got 3 and 3. So we're going to add 1 here. We've got 2 and 3. So over 2, up 3, add 1 there. This one's 0, 1, 0 and 1, add 1 there. 1 and 1, so add 1 here. 2 and 3, over 2, up 3, add another 1 here. 3 and 3, add another 1 here. That's 0 and 0, 0 and 1, over 0, up 1. And 1 and 2, over 1, up 2, and 2 and 3, over 2 and up 3. So that's the comparagram. All other values are 0. So you initialize the array to all zeros and then increment as appropriate. So now you've computed the comparagram. In other words, it's 0, 0, 3, 2, 0, 2, 1, 0. This is just tallies, totals. 2, 1, 0, 0, 1, 0, 0, 0. And so now, what is the meaning of the comparagram? So it's this array. Now often I've used x this way and y that way, but in matrices a lot of times your x-axis goes this way, your first axis goes this way, your last axis goes this way, so this whole thing would be rotated 90 degrees from where it is now. But depending on how you want to do it, as long as you're consistent. So now if you take this comparagram and you add together these values here, total everything, that's 5. This is 2 plus 1 is 3. This is 2 plus 1 is 3, and this is 1. So this is, if you total along here, and this, if you total this way, let's total here. This is equal to 3. This is equal to 3. If I total those, that's equal to 4. And this is equal to 2. Now, interestingly, if you take if you look at this, these numbers here, when I sum along rows here, are just the histogram of the one image, and these numbers here are the histogram of the other image. So these totaling along rows of the comparagram gives you the histogram of one image, and totaling down columns of the comparagram gives you the histogram of the other image. The other interesting thing to note is if you add up all these numbers, 2 plus 4 is 6, plus 3 plus 3 is another 6, is 12. And if you add up all these numbers, 5 plus 3 is 8, plus 3 plus 1, another 4, is 12. So the total is 12. So if you add up, of course, the entries in the histogram, you get the number of pixels. So in other words, just simply totalizing in this way gives you the number of pixels in the image. So this is an introduction to what is a comparagram. And now what I want to do is say, okay, this is a comparagram. And if you tried to fit data through this, you could see, well, it's really high here. It's like this. And so this is a comparagram. It's an array. A comparagram is a matrix. And this is a comparagraph. So the comparagraph is that smooth curve that fits through the points in the comparagram. The comparagraph is the graph of the comparametric equation. Likewise, I can introduce concepts like histogram, which is this discrete array, a list of numbers, and histograph, which is the smooth function underlying it. So if this was a histogram, I had 5, 3, 3, 1. That's your histogram. And your histograph is whatever that smooth function that passes through those points, the underlying function. So now we've got some terminology. Histogram, histograph, comparagram, comparagraph. So now we have what we need to, we have the tools we need in order to understand comparametric equations and have fun. So we're looking forward to having fun and learning some more about this. Thank you for visiting.